Lesson 14, inverse of a function. Inverse functions communicate the same data, but switch operations. So inverse functions communicate the same data, but they switch operations. For example, if a particular function relates the amount of air in a tire as a function of time, its inverse function would relate the amount of time needed for a particular level of tire inflation to be reached. So one example would be if a function relates the amount of air in a tire as a function of time, its inverse would relate the amount of time needed for one level of inflation or a particular level of inflation to be reached. The inverse of a function f of x is written as f raised to the negative 1 of x. So the inverse of a function f of x is written as f raised to the negative 1 of x. Also, the graph of the inverse of a function can be found by simply reflecting the graph of the original function over the line y equals x. Also the graph of the inverse function can be found by simply reflecting the graph of the original function over the line y equals x. Let's look at an example. So this is the original function. The original function, represented by the blue parabola, is reflected over the line y equals x to get the inverse relation. So the original function is the blue function, and you get it, it's y equals x squared. So you have the point 0, 0, 1, 1, 2, 4, and the same on the negative side. The green line represents the y equals x function, which is a linear function. We have points 1, 1, 2, 2, 3, 3, 4, 4, and the same on the negative side. And also the counterpoints on the negative side. To get the red function, which is the inverse function, we take every point on the blue function and we switch the x and y coordinates. That's the same as reflecting it over the line y equals x. So we take 1, 1, we switch x and y coordinates, it's still 1, 1. We take 2, 4, we switch the x and y coordinates, it becomes 4, 2. So we plot 4, 2 and we connect it with 1, 1 and with 0, 0. And we do likewise on the other side. And we connect it to get the inverse function. Note that the inverse of a function does not have to be a function. So note that the inverse of a function doesn't have to be a function. In the above graph, the inverse is a relation, not a function. So in the above graph, the inverse is a relation, not a function. So this is the inverse, and it's a relation, not a function. You can graph the inverse. You can tell this is a relation because it doesn't pass the vertical line test. If a vertical line is drawn through it, it touches the relation at more than one point. You can graph the inverse of a function by taking a few of the ordered pairs from the function and flipping the x coordinates with the y coordinates. You can graph the inverse of a function by taking a few of the ordered pairs from the function and flipping the x coordinates with the y coordinates, like we did for the blue and the red function. Then simply graph the new relation using the new set of ordered pairs. Then we simply graph the new relation using the new set of ordered pairs. You will see that it is the same as the original function, but it has been reflected over the line y equals x. So it's the same as the original function, but it's being reflected over the line y equals x. This is the same as the original function, but it's being reflected over y equals x. Since all the dependent variables are switched with the independent variables, you will notice that the domain and range of a function and its inverse are switched around. Since all the dependent variables are switched with the independent variables, you will notice that the domain and range of a function and its inverse are switched around. So you just have to switch the domain and range with its inverse to get the inverse domain and range. For example, in the above graph, the original function f of x equals x squared has domain x belongs to all real numbers and range y belongs to all real numbers, but y is not equal to 0. Sorry, y belongs to all real numbers, but y is greater than or equal to 0. That's because y the minimum y value is 0. So y is greater than belongs to all real numbers, but y is greater than or equal to 0. And x belongs to all real numbers. Therefore its inverse, to get the inverse, we simply switch the domain and the range. We have the domain and we take the range and we make it the domain. So x belongs to all real numbers, but x is greater than or equal to 0. And range, we take the domain and we make it the range. And range, y belongs to all real numbers. So we see here that the domain of the relation is x belongs to all real numbers, but x is greater than or equal to 0. X belongs to all real numbers, but x is greater than or equal to 0 because the minimum x value is 0. And range is y belongs to all real numbers because the relation goes up and down in both directions infinitely. This can be verified by checking the graph. So we can verify this by checking the graph. You may also be asked to write the inverse of a function algebraically. This is a simple procedure which consists of 4 steps. So this is a simple procedure consisting of 4 steps. First, make sure it is in y equals form instead of f of x form. If not, change it to this form. So first we make sure it's in y equals form instead of f of x form. If it's not, change it to that form. Then switch x and y in the equation. 2. Switch x and y in the equation. Keep everything else the same. So we switch x and y in the equation and we keep everything else the same. 3. Now solve for y. In other words, isolate y. So the third step is to solve for y. In other words, we isolate y. The fourth step is to lastly replace y with f raised to the negative 1 of x, denoting function notation. The fourth step is to lastly replace y with f raised to the negative 1 of x, denoting function notation. Let's go through an example. Given the function f of x equals 2x squared plus 6, find its inverse, g of x, algebraically. State if the inverse is also a function. So we have to state if the inverse is also a function. First we replace f of x with y. That's the first step. So the first step is to replace f of x with y. So we have f of x equals 2x squared plus 6. Now we have y equals 2x squared plus 6. Now we replace x and y. So we take every x and we switch it with every y. So we replace x and y. X equals 2y squared plus 6. Now we must isolate y. Subtract 6 from both sides. So now the next step is to isolate y. So we subtract 6 from both sides. X minus 6 equals 2y squared. Now we divide both sides by 2. So the next step is to divide both sides by 2. So y squared equals x minus 6 divided by 2. Now we complete the inverse operation of squaring. Because we need to isolate y. Note that the positive and negative square root must be considered. So we complete the inverse operation of squaring now. Note that the positive and negative square root must be considered. So we get y equals positive and negative square root of x minus 6 divided by 2. Lastly, we replace y with g of x. So the last step is to replace y with g of x. G of x equals positive or negative square root of x minus 6 divided by 2. The inverse of f of x, g of x. The inverse of f of x, g of x, is not a function because for any independent variable, there exists two dependent variables, a positive one and a negative one. So the inverse of f of x, g of x, is not a function because for any independent variable, any value of x, there exists two dependent variables, two values of y, a positive one and a negative one, because of the positive and negative square roots. That's all you need to know about calculating the inverse of a function. Just remember the 4 steps to algebraically find the inverse. So just remember the 4 steps to algebraically find the inverse. And that's all there is for lesson 14, inverse of a function. If you like this lesson, stay tuned for lesson 15, exponential growth. Also, if you like this lesson, be sure to like and subscribe, as well as leave a comment down below. Thank you.